we have you?
Yes.
Will we have you for pre-cal?
I don't know. I don't know. It does matter. You're going to be great. In both cases, you're going to have a great time. So, let's have a look at this, please. Quiet. Riley? Thanks. Okay, so what I want to be able to do, two things today. One thing I want to do is I want to look at how we can sketch a graph of a polynomial, and the key word here is sketch. We've talked about this before. Sketching a graph means we want to get just a rough functional idea of what this thing looks like. We're going to go a lot further with this in calculus. If we ever want to graph a function, meaning we want it to be a really accurate graph, of course, what are we now going to do in this day and age?
Calculator.
Graphic calculator or computer, for sure.
But does our graphing calculators deal with x's? Can they coordinate with x's? Because I don't know how to do that.
Well, okay. The question is, how do you get answers? I mean, can you get answers with x's in them? No, yours can't, but some can. When you go on to, and I don't know when we're going to make this break, but I think it's sort of time that we start to. Well, I don't want to open this can of worms, but I think that in a calculus class, ideally, it'd be nice to have a graphing calculator that is also a computer algebra system. So that would mean that in terms of Texas Instruments calculators, it would be the TI-89, which is my preference, or the TI Inspire CAS version. You don't have to do that.
How expensive?
The one you have now is the TI-84. They're a little bit of money.
I was told that we would only need our TI-84.
Well, and that's fine. You don't need anything more than that. But the advantage is, if you're going to go on, I got to be real brief here because I want to get on with this stuff. But those of you who are kind of looking into the future, if you're planning to go to college in a math-intensive area, you're going to want to probably, I would strongly recommend that you do upgrade, when you go to college at least. Because those calculators actually do things like, for example, they'll give you answers in terms of variables. You could ask those calculators literally to do things like in calculus, you could say, differentiate this function and give me the derivative function, and it will do it in terms of the variable.
Are we talking like, hey, mom, dad, birthday present coming up?
Yeah, well, here's the advantage. If you get, now I have to admit, I do not have a lot of experience, by a lot I mean any experience with the TI Inspires. I think they're really good calculators, but and I could be dead wrong on this. It seems like they're almost a little overkill. I really like the TI-89s. The TI-89s are easy to use, but just as powerful mathematically.
Are they colored?
The new ones might be. The Inspires are, the TI-89s, I should look and see. I'll look into this before you run out and get something. Let me look into it a little bit. But the advantage is, it's not required. By no means do you ever have to get one of these things, but the advantage would be that if you do get one, I can teach you how to use it. So, in calculus, there are some really interesting ways that you can use these things. It was, in McMinnville, when I taught calculus in McMinnville, it was sort of, I'm not kidding, for the last probably 5 years I taught it, every student had a TI-89.
Wow.
Which was kind of nice because we could do some things then that were, I don't expect you to though. So you don't run out and get one, you don't have to. But I just answered your question. No, the TI-84s do not answer things in terms of variables, but you don't need to for something like this anyway. If all you want to do is graph a function, I would just say y1 equals that, right? And it'll graph it for me in all the detail I would ever want. I can size the window like I need to. I can find the zeros. I can find the minima and maxima. I can do tons of stuff, even with the TI-84. It's still a really powerful machine. But you can also go further, and in college, you're very likely to use computers almost more than calculators, perhaps in some cases, like Mathematica or Maple software, which is really, really powerful computer algebra system software. Yeah. Yep, it'll be on your computer. It'll probably be your college will probably have it. And you'll probably get use of it just by enrolling in a class, for example. But my point is, not to expand this out too much. We're not graphing here. We're just sketching. Why do we sketch? Because a lot of times we don't really care what the function looks like. We just want to know what are the key features of the function. Yes?
What do you mean, like, what's the difference between, like, actually graphing and sketching?
A graph is exactly accurate, and a sketch is not. A sketch
Oh,
just
estimate.
has, like for example, I'll do a sketch.
Okay.
Let's sketch the function y equals x squared. Okay, if I sketch the function y equals x squared, really the important information is the vertex is where? 0, 0, 0 at the origin, and it opens up or down. That's a reasonable sketch of the,
Oh, okay.
right? See what I'm saying?
Yeah.
But I thought that with the 3, it goes up and down.
But this is x squared, right? This is, no, you're right, this isn't this one. I just
Okay.
sketched, just to give you an example of what sketching means, I just sketched that function.
Okay.
So a lot of times what we find is that the important features on a graph, the points that we're really looking for, are the x-intercepts, which we know how to find. That's an algebra issue. And that's, you know, what would the x-intercepts be for this function, or the zeros? 4, 1, -3. Boom, we got it. Okay, the other places though that a lot of times we want to find are some parts of the function that algebra is not good at telling us. And frankly, my strategy here is not to waste a lot of time doing this in a really ineffectual, wimpy way, when in 2 years we can do this efficiently and powerfully and not waste time. So I'm not going to have you, for example, try to find minima and maxima now, because it's just a really, I think it's a really dumb thing to do. It doesn't make any sense. You can't do it well. You can't do it well until you know some calculus. But what we do want to be able to do is just get an idea, kind of roughly speaking. We don't want the values of the minima and maxima, but we want to know kind of where they might sort of be, right? Between what 2 points would they exist? Now, I just threw out some words that you're not familiar with, though. So let's define those. When I say things like minima, and maxima, what is, somebody elaborate,
Same as
please.
minimum and maximum.
Okay, almost, plural, exactly, it's plural. So this is the plural of minimum. This is the plural, obviously, of maximum.
So it's not maximums and minimums? It's
Say- Say it again?
not minimums and maximums?
No, it's not. Just like you don't, I mean, sometimes, there's just some weird English words like that, and this is one of them. You know, it's minima and maxima means the set of more than one of those things. Okay, what are they? What is, can somebody describe for me what a minimum? Did I write those backwards? No, I didn't. What is a minimum? Yes,
Then when the graph is like this,
Yes.
and the maximum is
exactly. A
down.
minimum is what we drew up here, isn't it? Y equals x squared has a minimum because it has a point that is the lowest point around, at least in the vicinity,
So
right?
minimum is the point that's the lowest point around.
Yeah, a minimum is the lowest point in a neighborhood of values. And we'll get into what all that means in calculus more. But essentially, we're gonna even make it simpler than that. What is a maximum? What does it look like?
Upside down.
Okay, I'm gonna draw just a little representative function here that shows you about everything you need to know about minima and maxima. Okay. That function honestly tells you about everything you need to know about minima and maxima.
With the
Can somebody
points.
point to a maximum, please? Right there.
That sharp point.
First up top.
Okay, I heard somebody say there and somebody say there, and you're both right. These
And
are,
it needs to be a sharp point?
these are maxima. No, but it could be.
Okay, so
Okay.
you're just saying it could be either one.
Could be either one. Because it's the highest point in the vicinity, essentially, right?
Okay.
What we call this in calculus, technically, we'd call this a relative or a local maximum. Meaning that there might be other points out there far away that are higher than that, but in that immediate area, it's the highest point. Can somebody please point me to a minimum? Right there.
The bottom is
Okay,
the low.
there and there, good. Okay, so,
Do
There
they
and
have
there.
to be like equals this height?
no, not at all. Some can be higher than others. Can you describe, and what if you were trying to describe this to your younger brother or sister? What's a way that you might describe all maxima? They look like what?
The very top of the mountain.
Mountains. They look like peaks. That's it. They look like peaks. So, and that's a great way to think about it. A relative maximum is nothing more than a peak. If we graph the function, and the word that we use, not coincidentally, is topology. If you look at the topology of mathematics, it's like the landscape of a function. What does it look like? Well, in 2 dimensions, it just looks like a cross-section of mountain, right? 2-dimensionally, the topology we associate with the minimum is just a valley. There are only 2 different kinds of mountains that we could ever draw and 2 different kinds of valleys. One of them is a rounded mountain or a rounded valley, and one of them is jagged. We call these cusps, and we'll get into that in calculus. The conditions for where we find those things is really a calculus issue.
Do they really recede back into it?
Not necessarily.
Because that one receded in.
Well, no, it shouldn't. It should. That's not a function in it. It should just go. What I meant to draw, if I'd been a little more careful with this, probably would have drawn it more like that.
Okay.
Okay. Yeah. Yes, ma'am.
So if it says like find the maximum, would that be the highest point? Or
Yes. Yeah. And I'm going to ask you to do that on a graphing calculator because I'll show you how to do that on a graphing calculator. But once again, I'm not going to ask you to do that otherwise. There are some ways you could. With quadratics we could, because the vertex of a quadratic function of a parabola is always either a maximum or a minimum, right? So in some rare cases, yeah, we could find these things. But once again, for all intents and purposes, our bag of tools is really, really weak at this point for finding minima and maxima. That's really an issue that we'll just save for later. I just want you to know what they mean. And we can do some, indirectly, we can do some stuff around this that still is pretty cool. Yeah.
So one of those like peaks could be higher and they'd still be the minimum
Yes,
or maximum?
absolutely. Okay, and that's why in calculus we call them relative, meaning, why would we call this a relative maximum? It's a relative maximum because relative to the points around it, it's the highest,
Okay.
right? Now the ant walking along our 2-dimensional topology might walk over to a different part of the terrain and eventually climb a higher mountain. But this is still a mountain, right?
Yeah.
Okay?
Okay.
And so the other word we use is local. Local or relative maximum. Local meaning, in that vicinity. Relative meaning just compared to the points around it. Same idea though. Now the ones that we look at, because we're talking about polynomials, it's a characteristic of polynomials that once again we'll talk more about in a couple of years. But polynomials are well-behaved functions mathematically. And that is literally how we describe them. They don't violate any rules. They're really easy to work with. Polynomials, here's another math word. The further you get in math, the more descriptive the concepts become. Polynomials we would describe as being smooth, for example. They're smooth because they never have those kinds of jagged peaks. There are no cusps on a polynomial. They're always rounded and smooth. If you were to drag your hand along the edge of a polynomial, you're never going to cut it on this. Good. Right there. Okay, so and in calculus, what smooth we'll describe as being differentiable and continuous on an interval. That's for later. Okay, but for now, it just looks smooth. So we're only going to get these kinds of peaks and valleys. Okay. Now, we can't know what the coordinates are of those things, and we can't do a direct search for minima and maxima like we'll be able to in calculus, but we can do some stuff. We can still do some pretty cool stuff. So let's take this original function that we had, and let's see if we can sketch a graph of this thing. And when we sketch the graph, we are going to get some peaks and valleys.
Could they actually do a circle with the group?
Could they what?
Never mind. I probably missed something.
Okay, so how could we get a sketch of this thing? Now, you told me something important earlier. You told me the zeros. Yeah, good. You told me the zeros, and that's really key, actually. If I know where the zeros are.
And then is it going up because of the 1/10? Or
Well,
does that not affect
we'll
anything?
get to that. No, you're thinking about the right stuff.
What's the slope? No, are you on?
Okay, so we found the zeros. You told me the zeros were at -3, so right there, and at +1 and at +4, right? Okay. So are there any other zeros for this function?
No.
No, there are not, are there? There can't be any other zeros, or we would have found them, right? That is it. Those are the only three. So what are the possible things that are happening, let's say, between the leftmost zero and the middle zero? Yeah, it's either looping up or looping down, isn't it?
Yes.
Right? Okay, now the loop might be complicated or it might be simple, but it's looping up or down, right? For sure.
Yes.
How could we possibly test and see which one it's doing?
Plug in a number.
Plug in.
Plug in what we're going to call a test point. In calculus, we'll deal with these a lot, which is called a test point. So pick a value. What would be probably the best one to pick?
0.
0 in this case, because 0 is an easy one to substitute, and 0 is on that domain between the two functions, or between the two zeros, right? So now watch this closely, because this is a great trick. Do we really care what the value of the function is? We don't need to know, do we? If it's 10, it's up here somewhere. If it's negative 11, it's down here somewhere. But really, the 10 part and the 11 part wasn't what was important. What was important?
The negative which way?
The negative and positive. All we care about is the sign, especially if we're just doing a sketch, right? Now, later on in calculus, we'll be able to say, okay, well, let's actually identify where that point is. And in 2 years, we'll be able to say, okay, let's find the minima and maxima. And there is going to be, let's just pretend there's a maximum at -1, +3. So we could make a point there. And now our sketch gets a lot better. Now we're able to do something like that, at least on that one part, right? And it's much more accurate. It's really a very good sketch now. We can't do that yet. We don't know how to locate that exact point, but all we care about is that we just want to know, does it loop up or loop down to do our sketch? That's it. It's as far as we want to go this year.
What if it was like 2 maximums?
Okay, we'll get to that. You mean like if there's one here and one here?
Yeah, but then it would look like a down.
Okay, well, okay, no, you're onto something. That's actually a really good, hold that thought. We'll get to that.
So we
Okay.
can't tell how the incline of it is. That's what we're.
Well, not really, not really. And do you see why we can't do a very good job of that? Because if I pick an arbitrary point here, I don't know that I don't know if I got the peak or not. Right? If I pick a value at -1, and let's say I get back an answer of 3, well, is that the peak? Or is the peak way back here somewhere? I don't know. It might go up like this and kind of do something weird it might. Polynomials do things like that.
So it could have been a little short one or a big one. We're just wanting to know if
We
it's
did-
up or down.
We just want to know if it's up or down.
Okay.
Right. Our sketch is going to be very basic and rudimentary, but it'll get better in future years. For now, we just want to know loop up or loop down.
I don't understand the loop up or loop down.
Well,
Wouldn't it be doing both?
No. Loop. What I mean by loop up is this. That's what we're going to call just a loop up. This is what I'm calling a loop down.
Okay, but wouldn't it loop up on that first one and then loop down on the second one?
Maybe, but we're taking them one at a time.
Oh.
We're just looking for the first one right now. Okay? So on the first one, all I care about is the sign. I don't care about the value. So here's how I can do this really efficiently. I could do something like f of 0 equals. Now, notice that this is already in factored form. Obviously, we want to get this into factored form, don't we?
Is that what F means? It's like when factor.
No, out in front, you mean? No, f just means it's just our functional notation. F of x is just like a y, is all it is. Okay, so we need to get this. If we didn't start with this in factored form, we would have to factor it because that's how we find the zeros, correct?
Yes.
Okay? A lot of these I'm just going to give you in factored form because
Good.
really what we're practicing here is making the sketches. Of course, I wouldn't be me and you wouldn't be you if I didn't give you a couple where you have to do the whole ball of wax. But I won't make you do very many of those, right? Yeah, I want to give you the satisfaction of doing one of these problems all the way from basic
one?
principles, 1 or 2-ish, or 3-ish, something like that. Yeah.
Maybe 6.
No, I wouldn't do that to you. So, so what does this become then? Now, we've got this in factored form, and so all I really need to do, how many factors are there up there?
3,
No?
4.
All I need to do is just determine the signs of each of those factors and look at the product rule for those signs. See what I'm
You
saying?
have 2 positives and 2 negatives.
Right, well, okay, if I had 2 positives and 2 negatives, the result would be? Would be positive, wouldn't it? Because I'd have an even number of negatives being multiplied. What do I get here? When x is 0, the first factor is always, in this case, well, it's, what, 1/10 is positive or negative? Positive. Okay, so that sign is positive. What about the next factor? If I plug 0 in for x, I get
Positive.
positive. 0 plus 3 is positive, isn't it? Then next one, 0 minus 1 is negative. Last one is negative. The overall sign then would be
Positive.
positive. And so I know that it is looping up over here, don't I? Okay? So I'm going to put a plus sign right there to remind me that that's a positive intermediate value, test
How
value.
is positive the overall sign when there's two positives and negatives?
Well, okay, but so positive times positive is positive. Negative times negative is
Okay, so you
positive.
multiply them all together.
right. Multiply them all together. Remember that the easy way to tell is just count the number of negatives. If you have an even number of negatives, it's positive. An odd number of negative factors, it's always negative.
So
Yes.
if we had an odd number of negatives, they would have gone up down.
Correct. Yeah,
So
would have
it would
looped
be a
down.
minimum instead of a max.
Right.
Okay.
Okay, does that tell us anything about the next interval?
No.
It doesn't, does it? Or does it? Does it tell me?
That's just our first.
That's just the first one. That's all we found is right in here. Okay, do I know that the next one's gonna do that maybe?
No.
I don't really, do I? I don't. You might think that.
These are weird.
Well, they could be. What else could it do?
Go up
Back
again.
up again.
Yeah, it could do this, couldn't it? It could go,
Would it be a point?
But isn't there still like a minimum? Right
there would be. That would be a minimum then. You're right. Yeah. But we would see that on the graph that would be a
Could it
minimum.
go straight
It would
across
be.
there?
What do you mean?
Like, could it go from the second point and go straight along the x-axis at 0?
Come draw it. What you're saying.
Dry?
Come draw it.
I'm just saying, like, could it go from right here and then go?
Oh. Not unless it's a piecewise function. Yeah. So the polynomials would never do that. Yeah. Good question. Okay, so it could do either one, right? We don't know. How are we gonna find out?
Plug it in as one.
Plug in a test point. Exactly. So what's our next test point gonna be?
Let's do one.
Choose 0.
Don't you, could you do it like a 3?
I could do 3. I can't do 1 though. How come I can't do 1?
Because we're at 1.
Okay, because 1 is a 0, isn't it? I have to do a value between these. So I could do 3. That's fine. 3's great. We'll try 3. So f of 3 equals positive times
3. Yeah.
positive times positive times.
Oh, no.
So the overall sign is
Negative.
negative. Okay. Okay, are we done?
No.
Does that tell us everything we need to know?
Negative.
Yes. All that we
Are there?
can
Can
do.
anybody suggest another test point that we absolutely have to do?
0.
Pass.
Negative 3. Did it.
5.
5. 5. How come? 5's a good one. Why?
See where it's going to go afterwards.
Oh, see what it does afterwards. Because once again, it could do that, or it could do that. Right?
You have to pick one in between the two.
Yes. Yeah. The test points. You understand? The test points have to fall. We could do something like this. We could divide this up vertically into like sections, right? The test points have to go between or eventually outside of those divisions. Okay? Yes.
Okay, why did you switch the negative one, like in the green, to positive?
Well, because I'm plugging in a value of 3. So when I plug 3 into this factor here, now that becomes positive instead of negative.
Okay, that.
Okay? All right, so then we'll try 5. If we try 5, we're going to get positive times times times. So I get positive out here.
Do you want us to test the point before the whole
Yeah, we would need to do that also. We would have to test a value like -4, or -4 is fine. Sometimes, because these are integers, the zeros are all integers, it's really obvious. I mean, picking integer values makes evaluating the signs of the factors really simple. But what if those were things like square roots? Or they were things like fractions or something? Then what I always like to do is I like to pick a value, I call this the principle of exaggeration. I like to pick a value that makes it really obvious. Like for example, I could pick a value out here of like -1,000 negative 100 or something. And then it makes these signs of these things really obvious. You see what I'm getting at? Indicates that they're not such nice, conveniently packaged factors. Okay. And you're free to do that because all I need is a test point out there somewhere, right? Agreed?
Yep.
So we could do that, and what are we going to find? If I pick something like negative 10, what am I going to get? Positive times negative times negative times. How many negatives?
3.
3, so it's
Negative.
negative. And so we know what this thing looks like then. This guy just looks like
Hills. Hills.
yeah, right? Something like that. Yes, ma'am. Well,
It's a slanted
well,
thing.
it's right. It's just going to go. The end behavior is going to be
Forever, but it's
forever.
okay.
Yep. Now, what about that end behavior? Let's. I just love this stuff because it all kind of comes back together. If we look at the end behavior of this function, now what if we, and in real life, we would have started with a polynomial and then factored it. So we wouldn't even have to do this exercise, but it would have been replaced by the exercise of having to factor it in the first place. If I expanded this, what degree is this polynomial going to be?
Third.
It's going to be third, isn't it?
Why?
A third degree.
Because there's 3 x's.
3 x's. So if it's a third degree polynomial, now based on the work we've already done on end behavior, what did you notice about all of the even functions, the end behavior? Like x squared or x to the 4th. Okay, they go the same direction. Either they're both going up or they're both going down, right? Conversely, what did you notice about all of the odd functions? Yeah, they start up here and do wiggle around and go down there, or vice versa, right? And so this end behavior matches what we would expect, doesn't it? It's opposite on, the two ends have opposite behaviors because it's an odd function, right? See, isn't this cool how it all just kind of
Wait,
comes
what do you
together?
mean by on?
Well, because if I multiply this out, I'm just gonna get 1/10 x cubed plus a bunch of other junk, right? So the degree of the polynomial will be 3.
Oh, okay.
3 is odd, okay? Odd degree polynomials always have opposite end behavior. Cameron, turn around, please. Even degree polynomials always have the matching end behavior, both up, both down, okay? Okay, good, so we get the idea. Now, these aren't hard to do. All you're doing here is just finding the zeros and testing the endpoints, and that gives us a pretty good, accurate, reliable sketch. Okay, the next thing I want you to be able to do, though, this is really cool. I want you to be able to tell me what the minimum conceivable degree of that polynomial is. So if we wanted to, for example, try to fit this graph to a polynomial, we would want to be able to pick what's a good place to start.
3.
Yeah, okay. In this case, it'd be 3. Now let's compile kind of the pieces of information that we have available that will help us make this decision. Because some of it's pretty subtle. Some of it's really obvious, and some of it is a little bit subtle. But this is where you become good mathematicians if you can kind of pull all this stuff together. So one thing is, we know that the exact number of zeros for an nth degree polynomial, that meaning we're not going to specify, but if the degree of the polynomial is n, how many zeros does it have?
3.
It's got n for sure, right? It's always got n. Now, some of those, though, may not show up as x-intercepts, right? What are the things that could happen that would cause them not to show up as x-intercepts? If the zeros were imaginary, okay? There's another thing that could happen, too. You told me this is a third degree polynomial, right?
Yeah.
Because it's got 3 x-intercepts, and you're right, okay? But what if, now, what's going to happen if I do that? What's the degree of that one going to be? No,
3.
it's still 3. Why are those both 3, though? Do you see that they could be? Okay. How many of these, now, I have one real here. What happened to the other 2 zeros? They're imaginary, and that makes sense, because we said something else about the imaginary zeros. Imaginary zeros of a polynomial always come packaged how? In pairs, in complex conjugate pairs. That we can never get around that. They always come in complex conjugate pairs. So if I have, for example, a 5th degree polynomial, I've got 5 total zeros. How many of those could be real?
3.
Oh, 3 or 1 or 5, exactly. But because I know that if the imaginary ones have to come in pairs, then I could either have none or 0 or, none or 0. 0 or 2 or 4. If I have 0 imaginaries, all 5 of them are real. If I've got 2 imaginaries, that leaves 3 real. If I've got 4 imaginaries, it only leaves 1 real. Okay? But notice that there's no way I could have no real zeros. I'm always going to have at least one x-intercept. Isn't that consistent with what we just said about odd functions, though? If they have opposite end behaviors, they're going from positive infinity to negative infinity, they got to cross the x-axis at least once, don't they? Right? Okay, so that's all consistent. Here's the other thing that could happen, though. We could also get something like, and we talked a little bit about this the other day, we can get something like this. We'll just go back to x squared. Okay, what's the degree, obviously, what's the degree of that function?
1.
Can't be 1, because it's got to be 2, doesn't it? It's got to be 2. How come?
Because it's going the same way.
Okay, because the end behavior is matching. So it's got to be even, right? So the smallest possibility would be squared. Plus, we know that's a problem, right? Okay, but how many x-intercepts do you see? Okay, 1. But is it really 1? No.
It's 2 here.
It's really 2, isn't it? What's really happened here, remember, this is the thing. Didn't I do something where we talked about scraping the wire the other day?
Yeah.
Right, with the beads? That's it. If I pop this thing down a little bit, these x-intercepts are going to diverge. But when I pull this thing up so that these x-intercepts get closer and closer and closer together, they eventually converge on a single point. Okay, the point I want to make about this, and please pay close attention, because I really want you to kind of get a feel for this. And it's not going to show up in any math book or something, but this is just something that I think is important to know. When you see a 0 that is also a minimum or a maximum, in this case it's a minimum, but if the parabola opened down, it would be a maximum. It doesn't have to be a parabola. It could have been one of the loops on our even curvier polynomial, right? If one of the loops, if an x-intercept coincides with a minimum or a maximum, then didn't we play that little game where we scrape the beads together? Right? Okay, so what that tells us is, we know that the multiplicity of that 0 is greater than 1. We don't know what it is. It might be 4. But we don't, it might be 3, who knows? But it's not 1. Because if it's 1, the x-intercept is 1 like this, or this, or this, or this, where it's passing through the x-axis. Do you get that point? It's kind of a subtle point, right? But if it's just tangentially grazing, if the minimum and the 0 coincide, in other words, the beads have been scraped together, that means for sure it's at least counts for 2 x-intercepts, maybe more. Yep.
If it's a third degree polynomial and one of the loops hits the x-axis like that, but like how would that?
Okay, so that's a good question. So in other words, what if you're saying, what if like this is not the x-axis? What if that is?
Yeah.
Right. Okay. Once again, how many x-intercepts are there? Technically, there's only 2 different values, but technically it counts for 3. Because this one has a multiplicity higher than 1, right? Because the beads have been scraped together there. It's a minimum, see my point? It's a minimum and an x-intercept. You get that point? Okay. It's just, it's not like it's a make or break situation for you in the math class, but it's something that eventually it's going to be nice to know. Okay, there's another issue, though, that helps us out here also. There's another thing that makes this even a lot easier, and that is that the number of turning points, and a turning point in math just means a peak or a valley, right? The number of extrema, minima or maxima, and these are calculus words. We'll just call them turning points for now. The maximum number of turning points for an nth degree polynomial is, what do you think?
N.
Not n. N minus 1. Exactly. There's one, at very most, there is one less turning point than the degree of the polynomial. So this is kind of a classic looking third degree polynomial, right? Now we could make one that's degraded a little bit, like if we just look at the function x cubed. You might say it's simpler, and yeah it is, but it's also it's also what we might call a collapsed form or a degraded form, where it doesn't have all the humps, the turning points it normally would have. It just looks like that, where all we really did is we just took these two and we just kind of merged those two peaks and valleys together into one, right? So once again, it's just kind of another one of those bead scraping exercises. But we could still look at this and say, what's going to be the minimum degree of this polynomial?
0.
No.
3.
It's got to be 3. It's not a line, right? So it can't be 1.
Oh, yeah.
First degree polynomial would just be a line, so obviously it's not that. It can't be 2 because the end behavior is opposite, so the lowest it could be would be 3, right? Right? This one's pretty easy though, because we can count the 2 humps, right? This one now gets a little easier to see. How many turning points are there here? 1, so it's got to be at least degree 2, right? Okay, make sense?
Yep.
Okay, I'm going to throw a couple more at you here. How about, I'm going to make some of these really tricky. I'm going to challenge you. Okay, how about this one? How about this guy? What if we go... I want the minimum possible degree of that polynomial.
7. No.
5?
Yeah.
Okay, how come?
There's 4 turning points.
1, 2, 3, 4 turning points, even though how many x-intercepts are there? 1. If I extend the x-axis, just 1, right? Okay, and that's consistent. You told me 5. Does that match the end behavior?
Yes.
Yeah, opposite end behavior. Good. Okay, how about this guy? How about if we do? Okay, this will be a tricky one. Oh man, this will be tricky. Okay, get ready. Hold your hats. This is a.
One.
3.
No.
Trick question.
4th degree.
Okay, now I heard some people say. I heard people say, for example, 3. Okay, why not? Prove them wrong.
Or the scissors.
And behavior. Okay, I heard people say 2.
4.
Okay, now what's wrong with 2?
Because there's middle.
Okay, I'll fix that. Let's get rid of that middle hump, but I'm still saying there might be something wrong with 2. What if that middle hump goes
So
away?
is it 1 or is
Still
it 2?
4.
Okay, but why? This is a really tricky one. Defend yourself. Why is that?
Because the lines.
Okay.
Does it depend on his origin?
Well, let me ask you this. Sometimes it's easier to use a negative proof than a positive proof. So can we show why it can't be something rather than why it has to be something else? For example, it's only got 1 hump and 2 zeros. Now, those are characteristics of a parabola, right? Of a second degree polynomial, but what is obviously not parabolic about this? Okay, a parabola has to have, if you think back to Algebra 2, it has to have reflective symmetry, and this one does not, right? Make sense?
Can you say that if they can only have 1 minimum?
But
that one has 2.
well, but it actually doesn't. It's trying to have a minimum there, but it never actually becomes a minimum. See what I'm saying? And so, but just the fact that it's not symmetrical means it can't be a parabola. It can't be, right? So we'd have to and this is a pretty tough one. That book doesn't do anything even remotely like that. But I just want you to see, do you get why that would be the case?
Yes.
Okay? All right. Okay. I think I covered it all.
Well,
How
you
about
said when
some
you did
questions?
the other class,
Oh, that's right. Yeah, that's true. Yeah.
Wait, so, that one, so he's gonna be like telling what degrees and stuff?
Yeah, right. The assignment is really only going to have 2 kinds of problems. I'm going to ask you to do the first stuff we did. And here's what I'm going to do on Moodle. Oh, and I have to apologize in advance. I tried, but I've been so busy. We've had so much going on at school that I have not had the time, because these take forever. I haven't had the time to build my fancy new questions for this. So we're going old school Moodle on this one. What you're going to get is, essentially, you're just going to get, for a lot of these, you're going to get the question will have a lot of different choices, like 20 different choices for graphs, and you got to pick which one matches for example, the function that you're given. I mean, it's same, it's
Wait,
just
20?
still pretty cool, but it's not quite as cool. You guys just get
Wait,
spoiled.
were there 20?
I don't know, 16 or 20 or something. You just gotta, but how can you
Wait,
tell?
20 different pictures for one column?
Yeah, but that's not a big deal because
You can't.
if you're trying to find the, if you're trying to find a specific polynomial, you can find some identifying characteristics really easily. What might those be?
The vertices.
Well,
X's.
the x-intercepts,
That's what I meant
right?
to say.
And then you could find out if it's looping up or down between those, and you got it, right?
Seven on there now.
No, I'm putting it up though right away.
Wonderful.
Yes.
No rush. No rush.
Oh, come on now. It's always a rush to learn. Okay, you guys can just relax for a minute. I gotta take roll. James is here.